Atomic physics sounds a lot harder than it really is. Some of this you've had in chemistry, but this will look more at the mathematical element of the wave-particle duality of nature. Colorful lights similar to these in Denali National Park, Alaska, are commonly seen in the sky in northern latitudes. They are known as the aurora borealis, or the northern lights. The northern lights, which can extend thousands of kilometers, appear as arcs, bands, or streaks of color, sometimes flickering or pulsating. This is caused by billions of atomic jumps, as shown in the diagram. What to expect? In this chapter, you will learn about the development of the field known as quantum mechanics, which is required to describe phenomena at the atomic level where classical physics fails. The theory of quantum mechanics has led to many technological advances. For instance, it has enabled us to use nuclear energy and to perform life-saving MRIs. It also explains how the stars shine and why the northern lights occur. This photograph of the aurora borealis was taken in Denali National Park, Alaska. In the background are the Alaska Range Mountains. Auroras occur when electrically charged particles, mainly from the sun, become trapped in the Earth's atmosphere over the magnetic poles and collide with other atoms, resulting in the emission of visible light. Quantization of energy. Section 1 introduces the quantization of energy in black body radiation, and the photoelectric effect solves problems involving energy quanta, threshold frequency, and work function, and discusses the Compton shift as it pertains to the particle theory of light. Section 2, Models of the Atom, explores Rutherford's model of the atom, introduces emission and absorption spectra, explains atomic spectra in terms of Bohr's model of hydrogen, and evaluates the strengths and weaknesses of Bohr's model. Section 3, Quantum Mechanics, discusses the wave-particle duality of light and matter, shows how to calculate de Broglie's wavelengths, introduces the uncertainty principle, and describes the quantum mechanical picture of the atom. Standing waves occur when two waves of the same frequency, amplitude, and wavelength interfere as they travel through a medium in opposite directions. Light, in the wave model, consists of electromagnetic waves. Electromagnetic waves are transverse waves that consist of oscillating electric and magnetic fields at right angles to each other. Items to probe. Familiarity with atomic structure asks students to draw a schematic diagram of the atom. Preconceptions about the nature of light ask students to list arguments for and against the wave and particle theories of light. Preview of the chapter. There are 3 sections. Section 1 is broken into 2 subsections. Quantization of energy is broken into black body radiation and the photoelectric effect. Section 2, Models of the Atom, is broken into early models of the atom, atomic spectra, and the Bohr model of the hydrogen atom. Section 3 is broken into 4 subsections. The dual nature of light, matter, waves, the uncertainty principle, and the electron cloud. That's quantum mechanics, section 3. Section 1, quantization of energy. Explain how Planck resolved the ultraviolet catastrophe in black body radiation. Calculate energy of quanta using Planck's equation. Solve problems involving maximum kinetic energy, work function, and threshold frequency in the photoelectric effect. Figure 1, this molten metal has a bright yellow glow because of its high temperature. Black body radiation. By the end of the 19th century, scientists thought that classical physics was nearly complete. One of the few remaining questions to be solved involved electromagnetic radiation and thermodynamics. Specifically, scientists were concerned with the glow of objects when they reached a high temperature. All objects emit electromagnetic radiation. This radiation, which depends on the temperature and other properties of an object, typically consists of a continuous distribution of wavelengths from infrared, visible, and ultraviolet portions of the spectrum. The distribution of the intensity of the different wavelengths varies with temperature. At low temperatures, radiation wavelengths are mainly in the infrared region. So they cannot be seen by the human eye. As the temperature of an object increases, the range of wavelengths given off shifts into the visible region of the electromagnetic spectrum. For example, the molten metal shown in Figure 1 seems to have a yellow glow. At even higher temperatures, the object appears to have a white glow, as in the hot tungsten filaments of a light bulb, and then a bluish glow. Classical physics cannot account for black body radiation. One problem at the end of the 1800s was understanding the distribution of wavelengths given off by a black body. Most objects absorb some incoming radiation and reflect the rest. An ideal system that absorbs all incoming radiation is called a black body. Figure 2, light enters this hollow object through the small opening and strikes the interior wall. Some of the energy is absorbed by the wall, but some is reflected at a random angle. After each reflection, part of the light is absorbed by the wall. After many reflections, essentially all of the incoming energy is absorbed by the cavity wall. Only a small fraction of the incident energy escapes through the opening. Physicists study black body radiation by observing a hollow object with a small opening, as shown in Figure 2. Black body radiation, the radiation emitted by a black body, which is a perfect radiator and absorber, and emits radiation based only on its temperature. The system is a good example of how a black body works. It traps radiation. The light given off by the opening is in equilibrium with light from the walls of the object. Because the light has been given off and reabsorbed many times. Figure 3a, this graph shows the intensity of black body radiation at 3 different temperatures. Figure 3b, B, classical theory's prediction for black body radiation, the blue curve, did not correspond to the experimental data, the red data points, at all wavelengths, whereas Planck's theory, the red curve, did. Here is 3A and 3B together. Study the graphs, they will come in useful. Experimental data for the radiation given off by an object at 3 different temperatures is shown in Figure 3a. Note that as the temperature increases, the total energy given off by the body, the area under the curve, also increases. In addition, as the temperature increases, the peak of the distribution shifts to shorter wavelengths. Scientists could not account for these experimental results with classical physics. Figure 3b compares an experimental plot of black body radiation spectrum, the red data points, with the theoretical picture of what this curve should look like based on the classical theories, the blue curve. Classical theory predicts that as the wavelength approaches 0, the amount of energy being radiated should become infinite. This prediction is contrary to the experimental data, which show that as the wavelength approaches zero, the amount of energy being radiated also approaches zero. This contradiction is often called the ultraviolet catastrophe because the disagreement occurs at the ultraviolet end of the spectrum. Ultraviolet catastrophe, the failed prediction of classical physics that the energy radiated by a black body at extremely short wavelength is extremely large and that the total energy radiated is infinite. Experimental data for black body radiation support the quantization of energy. In 1900, Max Planck, 1858 to 1947, developed a formula for black body radiation that was in complete agreement with experimental data at all wavelengths. Planck's original theoretical approach is rather abstract in that it involves arguments based on entropy and thermodynamics. The arguments presented in this book are easier to visualize, and they convey the spirit and revolutionary impact of Planck's original work. Planck proposed that blackbody radiation was produced by submicroscopic electric oscillators, which he called resonators. He assumed that the walls of a glowing cavity were composed of billions of these resonators, all vibrating at different frequencies. Although most scientists naturally assumed that the energy of these resonators was continuous, Planck made the radical assumption that these resonators could only absorb and then give off certain discrete amounts of energy. When he first discovered this idea, Planck was using a mathematical technique in which quantities that are known to be continuous are temporarily considered to be discrete. After the calculations are made, the discrete units are taken to be infinitesimally small. Planck found that the calculations worked if he omitted this step and considered energy to come in discrete units throughout his calculations. With this method, Planck found that the total energy, En, of the resonators with frequency f is an integral multiple of hf as follows: En equals nhf. In this equation, n is a positive integer called a quantum number, and the factor h is Planck's constant, which equals 6.62606896 times 10 to the negative 34th joule seconds. To simplify calculations, we will use the approximate value of h equals 6.63 times 10 to the negative 34 joule seconds in this textbook. Here is another shot of 3B. You should become very familiar with this and look at the experimental data, Planck's theory, and the classical theory. Because the energy of each resonator comes in discrete units, it is said to be quantized, and the allowed energy states are called quantum states or energy levels. With the assumption that energy is quantized, Planck was able to derive the red curve shown in figure 3b on the previous page. Max Planck became president of the Kaiser Wilhelm Institute of Berlin in 1930. Although Planck remained in Germany during the Hitler regime, he openly protested the Nazi treatment of his Jewish colleagues and consequently was forced to resign his presidency in 1937. Following World War II, he was reinstated as president, and the institute was renamed the Max Planck Institute in his honor. According to Planck's theory, the resonators absorb or give off energy in discrete multiples of hf. Einstein later applied the concept of quantized energy to light. The units of light energy, called quanta, now called photons, are absorbed or given off as a result of electrons jumping from one quantum state to another. As seen by the equation above, if the quantum number n changes by 1 unit, the amount of energy radiated changes by hf. For this reason, the energy of a light quantum, which corresponds to the energy differences between two adjacent levels, is given by the following equation. A resonator will radiate or absorb energy only when it changes quantum states. The idea that energy comes in discrete units marked the birth of a new theory known as quantum mechanics. It says energy of light quantum, energy of quantum equals Planck's constant times frequency. If Planck's constant is expressed in units of joule seconds, the equation E equals hf gives the energy in joules. However, when dealing with the parts of atoms, energy is often expressed in units of electron volts. An electron volt is defined as the energy that an electron or proton gains when it is accelerated through a potential difference of 1 volt. Because 1 volt equals 1 joule per coulomb, the relation between the electron volt and the joule is as follows. 1 electron volt equals 1.60 times 10 to the negative 19 coulomb volts equals 1.60 times 10 to the negative 19 coulomb joules per coulomb equals 1.60 times 10 to the negative 19 joules. Planck's idea that energy is quantized was so radical that most scientists, including Planck himself, did not consider the quantization of energy to be realistic. Planck thought of his assumption as a mathematical approach to be used in calculations rather than a physical explanation. Therefore, he and other scientists continued to search for a different explanation of black body radiation that was consistent with classical physics. At the peak of the sun's radiation spectrum, each photon carries an energy of about 2.7 electron volts. What is the frequency of this light? All right, so here we are again. Given the energy, 2.7 electron volts, that's Planck's constant. That is the charge of an electron. Now the unknown is going to be the frequency. Use the equation for the energy of a light quantum and isolate frequency. There's E equals hf, f equals E over h, and now there is the conversion factor, f equals E over h. There's the givens and the constants. I'm going to plug in. Always be sure that your units cancel properly. In this problem, you need to convert energy from electron volts to joules. For this reason, 2.7 electron volts is multiplied by the conversion factor of 1.60 times 10 to the negative 19 joules per electron volts. Number 1, practice A. Assume that the pendulum of a grandfather clock acts as one of Planck's resonators. If it carries away an energy of 8.1 times 10 to the negative 15 electron volts in a 1 quantum change, what is the frequency of the pendulum? Note that an energy this small would not be measurable. For this reason, we do not notice quantum effects in the large-scale world. So there's the equation. There's solve for F, plug in, and the frequency is 2 hertz. A vibrating mass spring system has a frequency of 0.56 hertz. How much energy of this vibration is carried away in one quantum change? There's the equation for F. F equals E over H. E equals HF. There is the F, H, and Q. I'm going to plug in, solve for E. 3.7 times 10 to the negative 34th joules. A photon in a laboratory experiment has an energy of 5 electron volts. What is the frequency of this photon? So there are my equations, rearranged, of course. F equals E over H. List what I have, and then plug in and calculate. That's the frequency. Radiation emitted from human skin reaches its peak at a wavelength of 940 micrometers. What is the frequency of this radiation? List the equations. Now I'm going to list what I have, change it to meters, plug in, speed of light up top, and that's the frequency. What type of electromagnetic waves are these? Infrared. It's heat. How much energy in electron volts is carried by one quantum of this radiation? One quantum of this radiation. There's the equation, and I'll plug in. This is per quanta. The only real measurement is the frequency. Okay, 1.32 times 10 to the negative 3. A light beam shining on a metal, A, may eject electrons from the metal, B. Because this interaction involves both light and electrons, it is called the photoelectric effect. Question 1. Can one directly observe electrons being emitted from a metal surface? Can one directly observe electrons being emitted from a metal surface? No, electrons cannot be directly observed, but the effect of electrons leaving the metal surface can be detected because the metal becomes charged when it loses electrons. It becomes positively charged. Anything that becomes negatively charged or positively charged, it's because electrons are either leaving the surface of the object or they are going to the surface of the object. The photoelectric effect. As you learned in the chapter Electromagnetic Induction, James Maxwell discovered in 1873 that light was a form of electromagnetic waves. Experiments by Heinrich Hertz provided experimental evidence of Maxwell's theories. However, the results of some later experiments by Hertz could not be explained by the wave model of the nature of light. One of these was the photoelectric effect. The emissions of electrons from a material surface that occurs when light of certain frequency shines on the object of the material. When light strikes a metal surface, the surface may emit electrons, as Figure 4 illustrates. Scientists call this effect the photoelectric effect. They refer to the electrons that are emitted as photoelectrons. Classical physics cannot explain the photoelectric effect. The fact that light waves can eject electrons from a metal surface does not contradict the principles of classical physics. Light waves have energy, and if that energy is great enough, an electron could be stripped from its atom and have enough energy to escape the metal. However, the details of the photoelectric effect cannot be explained by classical theories. In order to see where the conflict arises, we must consider what should happen according to classical theory and then compare these predictions with experimental observations. Okay, next is going to be a table that that is dedicated to the photoelectric effect. Study it carefully, and hopefully it will help clear up some doubts you may have on the photoelectric effect. Albert Einstein, won the Nobel Prize on his paper on the photoelectric effect. As was stated in a chapter on waves, the energy of a wave increases as its intensity increases. Thus, according to classical physics, light waves of any frequency should have sufficient energy to eject electrons from the metal if the intensity of the light is high enough. Moreover, at lower intensities, electrons should be ejected if light shines on the metal for a sufficient time period. Electrons would take time to absorb the incoming energy before acquiring enough kinetic energy to escape from the metal. Furthermore, increasing the intensity of the light waves should increase the kinetic energy of the photoelectrons, and the maximum kinetic energy of any electron should be determined by the light's intensity. These classical predictions are summarized in the second column of Table 1. Scientists found that none of these classical predictions are observed experimentally. No electrons are emitted if the frequency of the incoming light falls below a certain frequency, even if the intensity is very high. This frequency, known as the threshold frequency, differs from metal to metal. If the light frequency exceeds the threshold frequency, the photoelectric effect is observed. The number of photoelectrons emitted is proportional to the light intensity. But the maximum kinetic energy of the photoelectrons is independent of the light intensity. Instead, the maximum kinetic energy of the photoelectrons increases with increasing frequency. Furthermore, electrons are emitted from the surface almost instantaneously, even at low intensities. See Table 1. Take a moment and review Table 1. It is related to what is on the next page. Einstein proposed that all electromagnetic waves are quantized. Albert Einstein resolved this conflict in his 1905 paper on the photoelectric effect, for which he received the Nobel Prize in 1921. By extending Planck's constant on quantization to electromagnetic waves, Einstein assumed that an electromagnetic wave can be viewed as a stream of particles, now called photons. A unit of quantum of light, a particle of electromagnetic radiation that has zero mass and carries a quantum of energy. Each photon has an energy, E, given by Planck's constant, E equals hf. In chemistry, you saw the equation as E equals h nu. In this theory, each photon is absorbed as a unit by an electron. When a photon's energy is transferred to an electron in a metal, The energy acquired by the electron is equal to hf. Threshold frequency depends on the work function of the surface. In order to be ejected from a metal, an electron must overcome the force that binds it to the metal. The smallest amount of energy the electron must have to escape the surface of a metal is the work function of the metal. Work function, the minimum energy needed to remove an electron from a metal atom. The work function is equal to hft, where ft is the threshold frequency for the metal. Photons with energy greater than hft eject electrons from the surface and from within the metal. Because energy must be conserved, the maximum kinetic energy of photons ejected from the surface is the difference between the photon energy and the work function of the metal. This relationship is expressed mathematically by the following equation. Maximum kinetic energy equals Planck's constant times the frequency of incoming photon minus the work function. Figure 5, this graph shows a linear relationship between the maximum kinetic energy of emitted electrons and the frequency of incoming light. The intercept with the horizontal axis is the threshold frequency. Study this carefully. Ft is the threshold frequency. According to this equation, there should be a linear relationship between F and Ke max, where H is a constant and the work function HFT is constant for any given metal. Some texts use the Greek letter phi to represent the work function. Such texts express the maximum kinetic energy of the photoelectron as Ke max equals HF minus phi. You may also see frequency represented by the Greek letter nu, leading to the expression Ke max equals H nu minus phi. Experiments have verified that this is indeed the case, as shown in figure 5. And the slope of such a curve, delta Ke over delta F, gives a value for H that corresponds to Planck's value. Sample problem B. Light of frequency of 1 times 10 to the 15th hertz illuminates a sodium surface. The ejected photoelectrons are found to have a maximum kinetic energy of 1.78 electron volts. Find the threshold frequency for this metal. I'm just going to run this through, and you can view it. And I'm not going to say anything. I'm just going to run it through and let it go. 5.7 times 10 to the 14th hertz, that's the Ft. In the photoelectric effect, it is found that incident photons with energy of 5 electron volts will produce electrons with a maximum kinetic energy of 3 electron volts. What is the threshold frequency of this metal? Aha, as they say when the plot's about to thicken. Same equation, solve for Ft. Let's plug in and solve. Thank goodness for calculators. It used to be a real hard thing to do calculations. Light of wavelength 350 nanometers falls on a potassium surface, and the photoelectrons have a maximum kinetic energy of 1.3 electron volts. What is the work function of potassium? What is the threshold frequency for potassium? All right, don't forget to change the nanometers to meters. Don't forget to put in the correction factor for the electron volts. There's the equation for frequency, the speed of light, charge of an electron or proton, and Planck's constant. Here's the work function. And that's it. 2.3 electron volts. And now let's calculate the FT given the work function of 2.3 electron volts, 5.6 times 10 to the 14th electron volts. Calculate the work function of sodium using the information given sample problem B. This is all the given. Equations. Plug in. And it's 3.78 times 10 to the negative 19th joules. Put that off to the side. Converting to electron volts. And I have 2.36 electron volts. Which of the following metals will exhibit the photoelectric effect when light of 7 times 10 to the 14th hertz frequency is shined on it? All right, that's what we need. Given and the equation. There's some givens. I have the HFT for lithium, silver, cesium. So let's just do the calculation and see which value works. How do you know what value works? Have you been paying attention out there? The photoelectric effect will be observed if E is greater than HFT. So that's your answer. E is greater. Now, this will hold true for lithium and cesium. Now let's do a conceptual challenge. Conceptual challenge 1, photoelectric effect. Even though bright red light delivers more total energy per second than dim violet light, the red light cannot eject electrons from a certain metallic surface, while the dimmer violet light can. How does Einstein's photon theory explain this observation? Number 2, photographs. Suppose a photograph were made of a person's face using only a few photons. According to Einstein's photon theory, would the result be simply a very faint image of the entire face? Why or why not? And third, glowing objects. The color of a hot object depends on the object's temperature. As temperature increases, the color turns from red to orange to yellow to white, and finally to blue. Classical physics cannot explain this color change, while quantum mechanics can. What explanation is given by quantum mechanics? All right, the answer is the photoelectric effect. Although there are more photons in the red light, each photon has a lower frequency than those that make up the violet light. Energy is proportional to frequency. So the photons of red light have less energy than the photons of violet light, and thus they cannot eject electrons from the surface. The photographs, no. The resulting photograph would show the image only at places where photons hit the film. As more photons are used, the dots become clearer or closer together, so the image eventually appears continuous. Glowing objects. Quantum mechanics predicts that as the energy increases, the frequency also increases, and the color of the glow changes accordingly. Aha, as they said when the plot is about to thicken. Aha. Photon theory accounts for observations of the photoelectric effect. The photon theory of light explains features of the photoelectric effect that cannot be understood using classical concepts. Did you know Einstein published his paper on photoelectric effect in 1905 while working in a patent office in Bern, Switzerland? In that same magical year, he published 3 other well-known papers, including the theory of special relativity. The photoelectric effect is not observed below a certain threshold frequency because the energy of the photon must be greater than or equal to the work function of the material. If the energy of the incoming photon is not equal to or greater than the work function, electrons will never be ejected from the surface, regardless of how many photons are present, how great the intensity is. Because the energy of each photon depends on the frequency of the incoming light, E equals HF. The photoelectric effect is not observed when the incoming light is below a certain frequency, FT. Above the threshold frequency, if the light intensity is doubled, the number of photons is doubled. This, in turn, doubles the number of electrons ejected from the metal. However, the equation for the maximum kinetic energy of an electron shows that the kinetic energy depends only on the light frequency and the work function, not on the light intensity. That is similar to the conceptual challenge. Very good. Thus, even though there are more electrons ejected, the maximum kinetic energy of individual electrons remains the same. Finally, the fact that the electrons are emitted almost instantaneously is consistent with the particle theory of light, in which energy appears in small packets because each photon affects a single electron. There is no significant time delay between shining light on the metal and observing electrons being ejected. Einstein's success in explaining the photoelectric effect by assuming that electromagnetic waves are quantized led scientists to realize that quantization of energy must be considered a real description of the physical world rather than a mathematical contrivance, as most had initially supposed. The discreteness of energy had not been considered a viable possibility because the energy quantum is not detected in our everyday experiences. However, scientists began to believe that the true nature of energy is seen in the submicroscopic level of atoms and molecules, where quantum effects become important and measurable. Figure 6a, when a photon collides with an electron. B, the scattered photon has less energy and a longer wavelength than the incoming photon. Study figure 6 carefully. Compton shift supports the photon theory of light. The American physicist Arthur Compton, 1892 to 1962, realized that if light behaves like a particle, then a collision between an electron and a photon should be similar to a collision between two billiard balls. Photons should have momentum as well as energy. Both quantities should be conserved in elastic collisions. So when a photon collides with an electron initially at rest in figure 6, the photon transfers some of its energy and momentum to the electron. As a result, the energy and frequency of the scattered photon are lowered. Its wavelength should increase. In 1923, to test his theory, Compton directed electromagnetic waves, X-rays, toward a block of graphite. He found that the scattered waves had less energy and longer wavelengths than the incoming waves, just as he had predicted. This change in wavelength, known as the Compton shift, provides support for Einstein's photon theory of light. Compton shift, an increase in the wavelength of a photon scattered by an electron relative to the wavelength of the incident photon. The amount that the wavelength shifts depends on the angle through which the photon is scattered. Note that even the largest change in wavelength is very small in relation to the wavelength of visible light. Go back and check out figure 6 based on the Compton shift explained here on this slide. For this reason, the Compton shift is difficult to detect using visible light, but it can be observed using electromagnetic waves with much shorter wavelength, such as X-rays. One photon bounces off electron, the electron absorbs energy, photon has longer wavelength after collision. Section review number 1. Describe the conflict known as the ultraviolet catastrophe. How did Planck resolve this conflict? How does Planck's assumption depart from classical physics? Classical physics predicts that radiation should increase as wavelength decreases, while experimental data shows that instead radiation increases, reaches a peak, and then decreases. Planck resolved this conflict by assuming that energy is quantized. In classical physics, energy is considered to be continuous. What is the energy in electron volts carried by one photon of violet light that has a wavelength of 4.5 times 10 to the negative 7 meters? What is the energy? All right, that's the equation for the energy. C equals lambda F. F equals C over lambda. E equals HC over lambda. And then put the Q in there for the conversion. Oh, that's the conversion. There she blows. And I'll just let this run. and the energy is 2.8 electron volts. What effects did scientists originally think that the intensity of light shining on a photosensitive surface would have on electrons ejected from that surface? How did these predictions differ from observations? A high-intensity source delivers energy to the surface more rapidly than a low-intensity source. Thus, the electron should receive the energy necessary to escape the surface sooner using the high-intensity source. However, electrons are ejected almost immediately from either source. A high-intensity light should also produce photoelectrons with greater kinetic energy. But observations show that the maximum kinetic energy of photoelectron depends on frequency rather than intensity. How does Einstein's theory that electromagnetic waves are quantized explain the fact that the frequency of light rather than the intensity determines whether electrons are ejected from photosensitive surface? If energy is delivered to electrons in packets, photons, whose energy depends on the frequency, then the intensity has no effect on whether photoelectrons are emitted. Light with a frequency of 1 times 10 to the 7th meter shines on tungsten, which has a work function of 4.6 electron volts. Are electrons ejected from the tungsten? If so, what is their maximum kinetic energy? There's the equation. There's lambda. Here's the plug-in, and the frequency is 3 times 10 to the 15th hertz. The work function there's HFT, Q, H. Plug in 1.1 times 10 to the 15th hertz. Okay, continuing with number 5. There's the conversion factor. FT from the prior slide. Q conversion and H. Plug in for E. 7.8 electron volts. Critical thinking is the number of photons in 1 joule of red light, 650 nanometers, greater than, equal to, or less than the number of photons in 1 joule of blue light, 450 nanometers. There are more photons in 1 joule of red light. A longer wavelength corresponds to a smaller frequency, and energy is proportional to frequency. Thus, there is less energy in each quantum of red light, and more quanta are needed to make up 1 joule. Section 2, Models of the Atoms. Explain the strengths and weaknesses of Rutherford's model of the atom. Recognize that each element has a unique emission and absorption spectrum. Explain atomic spectra using Bohr's model of the atom. Interpret energy level diagrams. In Thomson's model of the atom, electrons are embedded inside a larger region of positive charge, like seeds in a watermelon. That is the Thomson model. Early models of the atom. The model of the atom in the days of Newton was that of a tiny hard, indestructible sphere. This model was a good basis for the kinetic theory of gases. However, new models had to be devised when experiments revealed the electrical nature of atoms. The discovery of the electron in 1897 prompted J.J. Thomson, 1856 to 1940, to suggest a new model of the atom. In Thomson's model, electrons are embedded in a spherical volume of positive charge, like seeds in a watermelon, as shown in Figure 7. You can look back on Figure 7 and see how that looks. There are other names as well of Thomson's model. In this experiment, positively charged alpha particles are directed at a thin metal foil. Because many particles pass through the foil and only a few are deflected, Rutherford concluded that the atom's positive charge is concentrated at the center of the atom. Rutherford proposed a planetary model of the atom. In 1911, Hans Geiger and Ernest Marsden, under the supervision of Ernest Rutherford, 1871 to 1937, performed an important experiment showing the Thomson model could not be correct. In this experiment, a beam of positively charged alpha particles, which consists of 2 protons and 2 neutrons, was projected against a thin metal foil, as shown in Figure 8. Most of the alpha particles passed through the foil, as if it were empty space. Some of the alpha particles were deflected from their original direction through very large angles. Some particles were even deflected backwards. Such deflections were completely unexpected on the basis of the Thomson model. Rutherford wrote, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Such large deflections could not occur on the basis of Thomson's model, in which positive charge is evenly distributed throughout the atom, because the positively charged alpha particles would never come close to a positive charge concentrated enough to cause such a large angle deflection. Look back on it's called the gold foil experiment, and it was very famous. And consider the momentum of the alpha particle, looking at its speed and total mass. On the basis of his observations, Rutherford concluded that all of the positive charge in an atom and most of the atom's mass are found in the region that is small compared to the size of the atom. He called this concentration of positive charge, and mass the nucleus of the atom. Any electrons in the atom were assumed to be in a relatively large volume outside the nucleus. So according to Rutherford's theory, most alpha particles miss the nucleus of the atom entirely and pass through the foil, while only a few came close enough to the nuclei to be deflected. Let's look at another illustration. In Rutherford's model of the atom, electrons orbit the nucleus in a manner similar to planets orbiting the sun. This is the Rutherford model. Rutherford's model predicted that atoms are unstable. To explain why electrons in this outer region of the atom were not pulled into the nucleus, Rutherford viewed the electrons as moving in orbits about the nucleus, much like the planets orbit the sun, as shown in Figure 9. However, this assumption posed a serious difficulty. If the electrons orbited the nucleus, they would undergo a centripetal acceleration, according to Maxwell's theory of electromagnetism. Accelerated charges should radiate electromagnetic waves, losing energy. So, the radius of an atom's orbit would steadily decrease. This would lead to an ever increasing frequency of emitted radiation and a rapid collapse of the atom as electrons plunged into the nucleus. In fact, calculations show that according to this model, the atom would collapse in about 1/1000th of a second. This difficulty with Rutherford's model led scientists to continuing search for new models of the atom. Figure 10, when a potential difference is applied across an atomic gas in a tube. Here, hydrogen A, mercury B, and nitrogen C. The gas glows. The color of the glow depends on the type of gas. You can use goggles to see the spectrum of these elements. Atomic spectra. In addition to solving the problem with Rutherford's planetary model, scientists hoped that a new model of the atom would explain another mysterious fact about gases. When an evacuated glass tube is filled with a pure atomic gas and a sufficiently high potential difference is applied between metal electrodes in the tube, a current is produced in the gas. As a result, the tube gives off light, as shown in figure 10. The light's color is characteristic of the gas in the tube. This is how neon signs work. The variety of colors seen in neon signs is the result of the light given off by different gases in the tubes. Figure 11, each of these gases, hydrogen, mercury, and helium, has a unique emission spectra. And they're like fingerprints. They can identify the element. Each of these gases, hydrogen, mercury, and helium, have unique emission spectrum. This is additional view of figure 12. Each gas has a unique emission and absorption spectrum. When the light given off, emitted by an atomic gas, is passed through a prism, as shown in figure 11, a series of distinct bright lines is seen. Each line corresponds to a different wavelength or color of light. Such a series of spectral lines is commonly referred to as an emission spectrum. Emission spectrum, a diagram or graph that indicates the wavelength of radiant energy that a substance emits. As shown in figure 12, the emission spectrum for hydrogen, mercury, and helium are unique. Further analysis of other substances reveals that every element has a distinct emission spectrum. In other words, the wavelengths contained in a given spectrum are characteristic of the element giving off the light. Because no two elements give off the same line spectrum, it is possible to use spectroscopy to identify elements in a mixture. In addition to giving off light at specific wavelengths, an element can absorb light at specific wavelengths. The spectral lines corresponding to this process form what is known as an absorption spectra. Absorption spectra, a diagram or graph that indicates the wavelengths of radiant energy that a substance absorbs. An absorption spectrum can be seen by passing light containing all wavelengths through a vapor of the element being analyzed. Conceptual challenge, we have 3 again today. Neon signs, when a potential difference is placed across electrodes at the ends of a tube that contain neon, such as a neon sign. The neon sign glows. Is the light emitted by the neon sign composed of continuous spectrum or only a few lines? Energy levels. If a certain atom has 4 possible energy levels and an electron can jump between any 2 energy levels of the atom, how many different spectral lines could be emitted? Identifying gases. Neon is not the only type of gas used in neon signs. As you have seen, a variety of gases exhibit similar effects when there is a potential difference across them, while the colors observed are sometimes different. Certain gases do glow with the same color. How could you distinguish 2 such gases? All right, so we can use spectral tubes and look at the fingerprints of the gases. Neon signs. The light is composed of only a few lines because the spectrum contains only the lines corresponding to the electron transitions for the neon atom. Energy levels 6. E4 to E1, E3 to E1, E2 to E1, E4 to E2, E3 to E2, E4 to E3. Identifying gases, although 2 gases may glow with the same color, each atomic gas has unique spectrum that distinguishes it from any other element. Figure 13, hydrogen's dark absorption lines occur at the same wavelength as its bright emission lines. So the absorption and the emission spectra are essentially the same. If you look at the wavelengths, they're going to come out to be the same. Figure 13, visual strategy. Use this example to compare emission and absorption spectra. Okay, while we're preparing, look at the figure 13. How was the absorption spectrum produced? How was the absorption spectrum produced? A light source with a continuous spectrum was passed through hydrogen. Question 2. Why is most of the emission spectrum dark and most of the absorption spectrum bright? Well, in the absorption spectrum, it only absorbed hydrogen and left everything else. The emission spectrum is primarily dark because it consists only of the wavelengths that hydrogen emits. The absorption spectrum, on the other hand, is primarily bright because it contains light from a continuous source. Only the wavelengths that hydrogen absorbs are dim or even black. The absorption spectrum consists of a series of dark lines placed over the otherwise continuous spectrum. Each line in the absorption spectrum of a given element coincides with a line in the emission spectrum of that element, as shown in figure 13 for hydrogen. In everyday experience, more emission lines are usually seen than absorption lines. The reason for this will be discussed shortly. The absorption spectrum of an element has many practical applications. For example, the continuous spectrum of radiation emitted by the sun must pass through the cooler gases of the solar atmosphere and then through Earth's atmosphere. The various absorption lines seen in the solar spectrum have been used to identify elements in the solar atmosphere. Scientists are also able to examine the light from stars other than our sun in this fashion. With careful observation and analysis, astronomers have determined the proportions of various elements present in individual stars. Historically, the occurrence of atomic spectra was a great importance to scientists attempting to find a new model of the atom. Long after atomic spectra had been discovered, their cause remained unexplained. There was nothing in Rutherford's planetary model to account for the fact that each element has a unique series of spectral lines. Scientists hoped that a new model of the atom would explain this phenomena, and they wouldn't have to wait long. It actually came from someone who was Danish. The Bohr model of the hydrogen atom. In 1913, the Danish physicist Niels Bohr, 1885 to 1962, proposed a new model of the atom, hydrogen atom, that explained atomic spectra. Bohr's model of hydrogen contains some classical features and some revolutionary principles that could not be explained by classical physics. Bohr's model is similar to Rutherford's in that the electrons move in circular orbits about the nucleus. The electric force between the positively charged proton inside the nucleus and the negatively charged electrons is the force that holds the electron in orbit. However, in Bohr's model, only certain orbits are allowed. The electron is never found between these orbits. Instead, it is said to jump instantly from one orbit to another without ever being between orbits. Bohr's model further departs from classical physics by assuming that the hydrogen atom does not emit energy in the form of radiation when the electron is in any of these allowed orbits. Hence, the total energy of the atom remains constant. And one difficulty with the Rutherford model, the instability of the atom, is resolved. Bohr claimed that rather than radiating energy continuously, the electron radiates energy only when it jumps from an outer orbit to an inner orbit. The frequency of the radiation emitted in the jump is related to the change in the atom's energy. The energy of an emitted photon, E, is equal to the energy decrease of the atom, negative delta E atom, because delta E atom equals E final minus E initial. E equals negative delta E atom equals E initial minus E final. Planck's equation can then be used to find the frequency of the emitted radiation. E equals E initial minus E final equals HF. Figure 14a, when an photon is absorbed by an atom, an electron jumps to a higher energy level. B, when the electron falls back to a lower energy level, the atom releases a photon. In Bohr's model, transition between stable orbits with different energy levels accounts for the discrete spectral lines. The lowest state in the Bohr model, which corresponds to the smallest possible radius, is often called the ground state of the atom, and the radius of this orbit is called the Bohr radius. At ordinary temperatures, most electrons are in the ground state, with the electron relatively close to the nucleus. When light of a continuous spectrum shines on the atom, only the photons whose energy, HF, matches the energy separation between two levels can be absorbed by the atom. All right, make sure you go back and study figure 14. And here it is again. And it shows the incoming photon and the emitted photon and the jump of the electron. So study this carefully. This is the essence of the Bohr model. When this occurs, an electron jumps from a lower energy state to a higher energy state, which corresponds to an orbit farther from the nucleus, as shown in figure 14a. This is called an excited state. The absorbed photon accounts for the dark lines in the absorption spectrum. Once an electron is in an excited state, there is a certain probability that it will jump back to a lower energy level by emitting a photon, as shown in figure 14b. This process is known as spontaneous emission. The emitted photons are responsible for the bright lines in the emission spectrum. In both cases, there is a correlation between the size of an electron jump and the energy of the photon. For example, an electron in the fourth energy level could jump to the third level, the second level, or the ground state. Figure 15, every jump from one energy level to another corresponds to a specific spectral line. This example shows the transition that result in the visible spectral lines of hydrogen. The lowest energy level, E1, is not shown in this diagram. Figure 15, visual strategy. Explain all the arrows showing transitions between energy levels are represented relative to the E2 level. Also point out that this is a representation of the emission spectrum of hydrogen in the visible range only. This part of the hydrogen spectrum, the visible lines, is known as the Balmer series. Jumps from all levels to E1 emit ultraviolet radiation, which is not visible. Because Planck's equation gives the energy from one level to the next level, a greater jump means that more energy is emitted. Thus, jumps between different levels correspond to the various spectral lines that are observed. The jumps that correspond to the four spectral lines in the visible spectrum of hydrogen are shown in figure 15. Bohr's calculations successfully account for the wavelengths of all spectral lines of hydrogen. As noted earlier, fewer absorption lines than emission lines are typically observed. The reason is that absorption spectrum are usually observed when a gas is at room temperature. Thus, most electrons are in the ground state, so all transitions observed are from a single level, E1, to higher levels. Emission spectra, on the other hand, are seen by raising a gas to a high temperature and viewing downward transitions between any two levels. In this case, all transitions are possible, so more spectral lines are observed. Bohr's idea of the quantum jump between energy levels provides an explanation for the aurora borealis, or northern lights. Charged particles from the sun sometimes become trapped in the Earth's magnetic field and are deposited around the northern and southern magnetic poles. Light shows in southern latitudes are called aurora australis, or southern lights. When deposited, these charged particles from the sun collide with electrons of the atoms in our atmosphere and transfer the energy to these electrons, causing them to jump to a higher level. When an electron returns to a lower orbit, some of the energy is released as a photon. The northern lights are the result of billions of these quantum jumps happening at the same time. The colors of the northern lights are determined by the type of gases in the atmosphere. The charged particles from the sun are most commonly released from Earth's magnetic field into a part of the atmosphere that contains oxygen, which releases green light. Red lights are the result of collisions with nitrogen atoms. Because each type of gas releases a unique color, the northern lights contain only a few distinct colors rather than a continuous spectrum. An electron in a hydrogen atom drops from energy level 4 to energy level 2. What is the frequency of the emitted photon, and which line of the emission spectrum corresponds to this event? So it's going to go from 4 to 2. There it is, 4 to 2. Find the energy of the photon. The energy of the photon is equal to the change in the energy of the electron. The electron's initial energy level was E4, and the electron's final energy is E2. Using the values from the energy level diagram gives the following. E equals E initial minus E final. So it's going to be 2.55 electron volts. 2.55 electron volts. Note that the energies for each energy level are negative. The reason is that the energy of an electron in an atom is defined with respect to the amount of work required to remove the electron from the atom. In some energy level diagrams, the energy of E1 is defined as 0, and the higher energy levels are positive. In either case, the difference between the higher energy level and the lower one is always positive, indicating that the electron loses energy when it drops to a lower level. So there's the E. Use Planck's equation to find the frequency. And I want to rearrange that and put in the conversion factor. That's the conversion factor. And plug in. No, not yet. I want to rearrange it for F. My apologies. Now we want to plug in. Nope, we want to list the givens. Now we're going to plug in. Now we're ready. Those are the values. And the answer is 6.15 times 10 to the 14th hertz. Note that electron volts were converted to joules so that the units cancel properly. Find the corresponding line in the emission spectrum. Examination of the diagram shows that the electrons jump from level E4 to level E2. Corresponds to line 3 in the emission spectrum. Line 3. Evaluate your answer. Line 3 in the visible part of the electromagnetic spectrum and appears to be blue. The frequency equals 6.15 times 10 to the 14th hertz, lies within the range of the visible spectrum and is toward the violet end. So it is reasonable that light of this frequency would be visible blue light. Number 1. An electron in a hydrogen atom drops from energy level E3 to E2. What is the frequency of the emitted photon, and which line in the emission spectrum shown in sample problem C correspond to this event? At this time, you might want to review sample problem C. You know what I'm going to do? I'm going to put this on pause and I'm going to speed up these intermediate steps that I'm not narrating anyway. You can always put things on pause. I'll let this one go and then I will speed up the other ones. I'll make them 2 seconds instead of 4 seconds. And then F, you'll notice that 1.89 really is the only measurement. So that's the frequency, 4.56 times 10 to the 14th hertz. An electron in a hydrogen atom drops from energy level E6 to energy level E3. What is the frequency of the emitted photon? And in which range of the electromagnetic spectrum is this photon? See Table 1 in the chapter Light and Reflection. for ranges in the electromagnetic spectrum. And it's 2.73 times 10 to the 14th hertz. The energy level diagram in figure 16 shows the first 5 energy levels for mercury vapor. The energy of E1 is defined as 0. What is the frequency of the photon emitted when an electron drops from energy level 5 to 1 in a mercury atom? Now I have it on 2 seconds, and it'll be done in a moment. And the answer is 1.61 times 10 to the 15th hertz. You can go to the chapter on light and reflection. It's very near the beginning of the chapter. It's the first table in the chapter, and see where on the electromagnetic radiation spectrum these frequencies fall. How many different spectral lines could be emitted if mercury vapor were excited by photons with 6.67 electron volts of energy? Hint, an electron could move, for example, from energy level 5 to 3, then from 3 to 2, and then from 2 to 1. 10. Number 5, the emission spectrum of hydrogen has one emission line at the frequency of 7.29 times 10 to the 14th hertz. Calculate which two energy levels electron must jump between to produce this line, and identify the line in the energy level diagram in sample problem C. Hint, first find the energy of the photons, and then use the energy level diagram. All right, let's put down what's given. (4.83 times 10 to the 19th joules). That's the energy. Then I'm going to multiply that by the conversion factor for electron volts, and I get 3.02 electron volts. And that's E6 to E2, line 1. Bohr's model is incomplete. The Bohr model of hydrogen was a tremendous success in some aspects because it explained several features of the spectrum of hydrogen that had previously defied explanation. Bohr's model gave an expression for the radius of the atom and predicted the energy levels of hydrogen. This model was also successful when applied to hydrogen-like atoms, that is, atoms that contain only one electron. But while many attempts were made to extend the Bohr model to multi-electron atoms, the results were unsuccessful. Bohr's model of the atom also raised new questions. For example, Bohr assumed that electrons do not radiate energy when they are in a stable orbit, but his model afforded no explanation for this. Another problem with Bohr's model was that it could not explain why electrons always have certain stable orbits, while other orbits do not occur. Finally, the model followed classical physics in certain respects, but radically departed from classical physics in other respects. For all of these reasons, Bohr's model was not considered to be a complete picture of the structure of the atom, and scientists continued to search for a new model that would resolve these difficulties. Section review. Number 1, based on the Thomson model of the atom, what did Rutherford expect to happen when he projected positively charged alpha particles against a metal foil? If positive charges were spread throughout the atom, as in Thomson's model, the alpha particles would be deflected slightly at most. Why did Rutherford conclude that an atom's positive charge and most of its mass are concentrated in the center of the atom? Because the alpha particles literally bounce back, and taking momentum into account, that was like a 15-inch shell being shot at something in tissue paper and bouncing back, because most particles were not deflected at all, while a few were sharply deflected. Sharply is putting it mildly. But it did prove that it's mostly empty space and that there is an incredible concentration of nuclear material at the center of the atom. What are two problems with Rutherford's model of the atom? It predicted an unstable atom, and it couldn't explain spectral lines. How could the atomic spectra of gases be used to identify the elements present in distant stars? Because spectral lines are unique to each element, an analysis of the spectra would reveal what elements are present. Bohr's model of the atom follows classical physics in some respects and quantum mechanics in others. Which assumptions of the Bohr model correspond to classical physics, which correspond to quantum mechanics? Classical physics, the electron orbits the nucleus, electrons radiate energy. Quantum mechanics, only certain orbits are allowed. The electron radiates energy only when it jumps between levels. Energy radiated depends on the difference between energy levels. How do Bohr's model of the atom account for the emission and absorption of spectra of an element? Each line corresponds to a jump from one energy level to another. A Norwegian scientist, Lars Vigard, determined the different wavelengths that are present or part of the northern lights. He found that only a few wavelengths of light rather than a continuous spectrum are present in the lights. How does Bohr's model of the atom account for this observation? The electrons can jump only from one allowed orbit to another. Only lines that correspond to these jumps are found in the spectral lines. Section 3, Quantum Mechanics, recognize the dual nature of light and matter, calculate the de Broglie wavelength of matter waves, distinguish between classic ideas of measurement and Heisenberg's uncertainty principle, describe the quantum mechanical picture of the atom, including the electron cloud and probability waves. The dual nature of light, as discussed in section 1. There is considerable evidence for the photon theory of light. In this theory, all electromagnetic waves consist of photons, particles like pulses that have energy and momentum. On the other hand, light and other electromagnetic waves exhibit interference and diffraction effects that are considered to be wave behaviors. Language of physics, modern physics has introduced ideas that may conflict with intuition and common sense. The dual nature of light is one example. Although the words particle and wave are familiar, students need to think about them in a new way when dealing with atomic and subatomic phenomena. So which model is correct? We will see that each is correct and that a specific phenomena often exhibits only one or the other of these natures of light. Light is both a wave and a particle. Some experiments can be better explained or only explained by the photon concept, whereas others require the wave model. Most physicists accept both models and believe that the true nature of light is not describable in terms of a single classical picture. For example, for an example of how photons can be compatible with electromagnetic waves, consider radio waves at a frequency of 2.5 megahertz. That's 2.5 times 10 to the sixth hertz. The energy of a photon having this frequency can be found using Planck's equation as follows. E equals Planck's constant times 2.5 times 10 to the sixth hertz, and the energy is 1.7 times 10 to the negative 27 joules. From a practical point of view, this energy is too small to be detected as a single photon. A sensitive radio receiver might need as many as 10 to the 10th, that's a billion is 10 to the ninth, of these photons to produce a detectable signal. With such a large number of photons reaching the detector every second, we would not be able to detect the individual photons striking the antenna. Thus, the signal would appear as a continuous wave. Now consider what happens as we go to higher frequencies and hence shorter wavelengths. In the visible region, it is possible to observe both the photon and the wave characteristic of light. As we mentioned earlier, a light beam can show interference phenomena and produce photoelectrons. The interference phenomena are best explained by the wave model of light, while the photoelectrons are best explained by the particle theory of light. At even higher frequencies and correspondingly shorter wavelengths, the momentum of energy of the photon increases. Consequently, the photon nature of light becomes very evident. In addition, as the wavelength decreases, wave effects such as interference and diffraction become more difficult to observe. Very indirect methods are required to detect the wave nature of very high frequency radiation, such as gamma rays. Thus, all forms of electromagnetic radiation can be described from 2 points of view. At one extreme, the electromagnetic wave description suits the overall interference pattern formed by a large number of photons. At the other extreme, the particle description is more suitable for dealing with highly energetic photons of very short wavelengths. Matter waves. In the world around us, we are accustomed to regarding things such as thrown baseballs solely as particles, and things such as sound waves solely as forms of wave motion. As already noted, this rigid distinction cannot be made with light, which has both wave and particle characteristics. In 1924, the French physicist Louis de Broglie, 1892 to 1987, extended the wave-particle duality. In his doctoral dissertation, de Broglie proposed that all forms of matter may have both wave properties and particle properties. At that time, this was a highly revolutionary idea with no experimental support. Now, however, scientists accept the concept of matter's dual nature. The concept of matter waves is probably new and unusual to most students because students have no experience with matter waves. They may not understand the nature of such waves. The meaning of de Broglie's hypothesis is that we may picture the electron in two ways: as a particle in motion, or as a wave occupying a certain region of space. Encourage students to discuss their mental images of electron waves to prepare them for the probability interpretation of matter waves. Also, assure them that these ideas remain puzzling to many people. The wavelength of a photon is equal to Planck's constant h divided by the photon's momentum p. De Broglie speculated that this relationship might also hold true for matter waves as follows. Wavelength of matter waves, de Broglie's wavelength equals Planck's constant over momentum. As seen by this equation, the larger the momentum of an object, the smaller the wavelength. In an analogy with photons, de Broglie postulated that the frequency of a matter wave can be found with Planck's equation as illustrated below. Frequency of matter wave, frequency equals E over h. De Broglie's frequency equals energy divided by Planck's constant. The dual nature of matter suggested by de Broglie is quite apparent in these two equations, both of which contain particle concept E and mv and wave concepts of lambda and f. A, electrons show interference patterns similar to those of B, light waves. This demonstrates that electrons sometimes behave like waves. And there is certainly experimental evidence. At first, de Broglie's proposal that all particles also exhibit wave properties was regarded as pure speculation. If particles such as electrons had wave properties, then under certain conditions they should exhibit interference phenomena. 3 years after de Broglie's proposal, C.J. Davison and L. Germer of the United States discovered that electrons can be diffracted by a single crystal of nickel. This important discovery provided the first experimental confirmation of the de Broglie theory. An example of electron diffraction compared with light diffraction is shown in figure 17. Electron diffraction by a crystal is possible because the de Broglie wavelength of a low energy electron is approximately equal to the distance between atoms in a crystal. In principle, diffraction effects should be observable even for objects in our large-scale world. Louis de Broglie's doctoral thesis about the wave nature of matter was so radical and speculative that his professors were uncertain about whether they should accept it. They resolved the issue by asking Einstein to read the paper. Einstein gave his approval, and de Broglie's paper was accepted. 5 years after his thesis was accepted, de Broglie won the Nobel Prize for his theory. However, the wavelength of material objects in our everyday world are much smaller than any possible aperture through which the object could pass. With what speed would an electron with a mass of 9.109 times 10 to the negative 31st kilograms have to move if it had a de Broglie wavelength of 7.28 times 10 to the negative 11th meters? All right, list the givens. It's going to go quite fast here. Use the equation for the de Broglie wavelength and isolate V. There's the equation that's given, that's the plug-in, that's the answer. 1 times 10 to the 7th meters per second. That's pretty fast. With what speed would a 5-kilogram rock have to be thrown if it were to have a wavelength of 3.32 times 10 to the negative 34 meters? With what speed would a 50-gram rock have to be thrown? .40 meters per second. If the de Broglie wavelength of an electron is equal to 5 times 10 to the negative 7th meters, how fast is the electron moving? How fast is the electron moving? Here again is another calculation on de Broglie wavelength. And it's going to be 1,460 meters per second. How fast would one have to throw a 0.15 kilogram baseball if it were to have a wavelength of 5 times 10 to the negative 7th meters, the same wavelength as the electron in problem 2? This will be fascinating. (8.84 times 10 to the negative 27th meters per second). Not very fast at all. What is the de Broglie wavelength of a 1,375 kilogram car traveling at 43 kilometers per hour? Four times 10 to the negative 38 meters. A bacterium moving across a petri dish at 3.5 micrometers per second has a de Broglie wavelength of 1.9 times 10 to the negative 13 meters. What is the bacterium's mass? (1.0 times 10 to the negative 15 kilograms. De Broglie's hypothesis that there is always an integral number of electron wavelengths around each circumference explains why only certain orbits are stable. De Broglie wave account for the allowed orbits of Bohr's model. At first, no one could explain why only some orbits were stable. Then, de Broglie saw a connection between his theory of the wave character of matter and the stable orbits in the Bohr model. De Broglie assumed that an electron orbit would be stable only if it contained an integral whole number of electron wavelengths, as shown in figure 18. The first orbit contains one wavelength, the second orbit contains two wavelengths, and so on. De Broglie's hypothesis compares with the example of standing waves on a vibrating string of a given length, as discussed in the chapter Vibrations and Waves. In this analogy, the circumference of the electron's orbit corresponds to the string's length. So the condition for an electron orbit is that the circumference must contain an integral multiple of electron wavelengths. The uncertainty principle. In classical mechanics, there is no limitation to the accuracy of our measurements in experiments. In principle, we could always make a more precise measurement using a more finely detailed meter stick or a stronger magnifier. This unlimited precision does not hold true in the quantum mechanics. The absence of such precision is not due to the limitations of our instrument or to our perturbation of the system when we make measurements. It is a fundamental limitation inherent in nature due to the wave nature particles. Simultaneous measurements of position and momentum cannot be completely certain. In 1927, Werner Heisenberg argued that it is fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. In fact, the more we learn about a particle's momentum, the less we know of its position. And the reverse is also true. This principle is known as Heisenberg's uncertainty principle. Uncertainty principle, the principle that states that it is impossible to simultaneously determine a particle's position and momentum with infinite accuracy. Figure 19a, the electron is viewed before colliding with the photon. B, the electron recoils, is disturbed as the result of the collision with the photon. Study carefully figure 19 related to Heisenberg's uncertainty principle. To understand the uncertainty principle, consider the following thought experiment. Suppose you wish to measure the position and momentum of an electron as accurately as possible. You might be able to do this by viewing the electron with a powerful microscope. In order for you to see the electron and thus determine its location, at least one photon of light must bounce off the electron and pass through the microscope into your eye. This incident photon is shown moving towards the electron in figure 19a. When the photon strikes the electron, as in figure 19b, it transfers some of its energy and momentum to the electron. So, in the process of attempting to locate the electron very accurately, we become less certain of its momentum. The measurement procedure limits the accuracy to which we can determine position and momentum simultaneously. The mathematical form of the uncertainty principle states that the product of the uncertainties in position and momentum will always be larger for some minimum value. Arguments similar to those given here show that this minimum value is Planck's constant, divided by 4 pi. Thus, delta x times delta p is greater than or equal to h over 4 pi. In this equation, delta x and delta p represent the uncertainty in the measured values of a particle's position and momentum, respectively, at some instant. This equation shows that if delta x is made very small, delta p will be large, and vice versa. The electron cloud, 1926, Erwin Schrödinger, proposed a wave equation that described the manner in which de Broglie's matter wave change in space and time. Although this equation and its derivations are beyond the scope of this book, we will consider Schrödinger's equation qualitatively. Solving Schrödinger's equation yields a quantity called the wave function, represented by the Greek letter psi. A particle is represented by the wave function psi that depends on the position of the particle and time. An electron's location is described by a probability distribution. As discussed earlier, simultaneous measurements of position and momentum cannot be completely certain. As we continue, because the electron's location cannot be precisely determined, it is useful to discuss the probability of finding the electron at different locations. It turns out that the quantity, absolute value of psi squared, is proportional to the probability of finding the electron at a given position. Read below. This interpretation of Schrödinger's wave function was first proposed by the German physicist Max Born in 1926. Did you know, although Einstein was one of the founders of quantum theory, he did not believe that it could be a final description of nature. His conviction in this matter led to his famous statement, "In any case, I am convinced that he, God, does not play dice." Figure 20 shows the probability per unit distance of finding the electron at various distances from the nucleus in ground state, the ground state of hydrogen. The height of the curve at each point is proportional to the probability of finding the electron, and the x-coordinate represents the electron's distance from the nucleus. Note that there is a non-zero probability of finding the electron in the nucleus. The peak of this curve represents the distance from the nucleus at which the electron is most likely to be found in the ground state. Schrödinger's wave equation predicts that this distance is 5.3 times 10 to the negative 11th meters, which is the value of the radius of the first electron orbit in Bohr's model of hydrogen. Figure 20. The height of this curve is proportional to the probability of finding the electron at different distances from the nucleus in the ground state of hydrogen. Study that carefully. We're actually very close to the end of the chapter. Quantum mechanics also predicts that the wave function for the hydrogen atom in the ground state is spherically symmetrical. Hence, the electron can be found in a spherical region surrounding the nucleus. This is in contrast to the Bohr model, which confines the position of the electron to points in a plane. This result is often interpreted by viewing the electron as a cloud surrounding the nucleus, called an electron cloud. The density of the cloud at each location is related to the probability of finding the electron at that location. The most probable distance for an electron's location in the ground state is equal to the first Bohr radius. Analysis of each of the energy levels of hydrogen reveals that the most probable electron location in each case is in agreement with each of the radii predicted by the Bohr model. The discrete energy levels that could not be explained by Bohr's theory can be derived from Schrödinger's wave equation. In addition, the de Broglie wavelengths account for the allowed orbits that were unexplainable in Bohr's theory. Thus, the new quantum mechanical model explains certain aspects of the structure of the atom that Bohr's model could not account for. Although probability waves and electron clouds cannot be simply visualized as Bohr's planetary model could, they offer a mathematical picture of the atom that is more accurate than the Bohr model. The material presented in this chapter is only an introduction to quantum theory. In fact, it forms the basis for understanding the structure of all known atoms and the existence of all molecules. Although most scientists believe that quantum mechanics may be nearly the final picture of the deepest levels of nature, a few continue to search for other explanations, and debates about the implications of quantum mechanics continue. Is light considered to be a wave or a particle? Explain your answer. Light exhibits some aspects that are characteristic of classical waves and others that are characteristic of classical particles. It's called the wave-particle duality of the nature of light. How did de Broglie account for the fact that the electrons in Bohr's model are always found at certain distinct distances from the nucleus? The allowed orbits are those that contain an integral number of electron wavelengths. Calculate the de Broglie wavelength of a proton moving at 1.00 times 10 to the fourth meters per second. Here is the givens. Velocity, mass, and Planck's constants. That's the equation, and now we're off. Plug in and solve. 3.96 times 10 to the negative 11th meters. What is the physical significance of the square of the Schrödinger wave function? It is proportional to the probability of finding the electron at a given position. Why is the electron sometimes viewed as an electron cloud? It's really a probability cloud, because the electron is found in a spherical region surrounding the nucleus, and its location is not known with complete certainty. critical thinking. In classical physics, the accuracy of measurements has always been limited by the measuring instruments used, and no instrument is perfect. How is this limitation different from that formulated by Heisenberg in the uncertainty principle? Even with perfect measuring instruments according to the Heisenberg uncertainty principle, simultaneous measurements of position and momentum cannot be completely certain. In fact, the smaller the uncertainty is in one of these quantities, the larger is the minimum uncertainty in the other quantity. This inherent limitation is a result of the wave nature of matter. Key ideas, Section 1, quantization of energy. Blackbody radiation and the photoelectric effect contradict classical physics, but they can be explained with the assumption that energy comes in discrete units or is quantized. The energy of a light quantum of photon depends on the frequency of light. Specifically, the energy of a photon is equal to frequency multiplied by Planck's constant. Planck's constant h is approximately equal to 6.63 times 10 to the negative 34 joule seconds. Key ideas, Section 1, quantization of energy continued. The relation between the electron volt and the joule is as follows. 1 electron volt equals 1.60 times 10 to the negative 19 joules. The minimum energy required for an electron to escape from a metal depends on the threshold frequency of the metal. The maximum kinetic energy of photoelectrons depends on the work function and the frequency of the light shining on the metal. This is Section 2, Models of the Atom. Rutherford's scattering experiment revealed that all of an atom's positive charge and most of the atom's mass are concentrated at its center. Each gas has a unique emission and absorption spectrum. Atomic spectra are explained by Bohr's model of the atom, in which electrons move from one energy level to another when they absorb or emit photons. Section 3, quantum mechanics. Light has both wave and particle characteristics. De Broglie proposed that matter has both wave and particle characteristics. Simultaneous measurements of position and momentum cannot be made with infinite accuracy.